This is the supergiant Cableway installation, a breathtaking process where human precision challenges gravity itself. Today, we go behind the scenes of one of the most complex construction processes on Earth, revealing how America builds high-tech ropeways across mountains and megaprojects with mind-blowing precision. And before we rise into this world of steel and sky, make sure to like, subscribe, and hit the bell, because what you're about to witness will forever change how you see infrastructure. Long before these systems became symbols of tourism and modern engineering, their roots were born from necessity. In the late 19th century, miners and loggers struggling in the rugged landscapes of Colorado, Montana, and the Pacific Northwest faced terrain so hostile that horses, wagons, and even railways could not survive. In response, early innovators began stretching crude steel cables between cliffs, using primitive pulleys and steam-powered winches to move timber and ore across impossible slopes. These early contraptions were dangerous and unstable, yet they became lifelines for industries that would otherwise collapse. Over time, as America's appetite for exploration and development grew, these simple cable systems evolved into the foundations of what would become the modern ropeway industry. By the 1930s, a new purpose emerged. The rise of winter tourism and mountain recreation transformed cableways from industrial tools into passenger systems. Ski resorts realized that efficient uphill transportation could define an entire seasonal economy. The installation of the first modern ski lift at Sun Valley marked a turning point, pushing ropeway technology into the public eye. As decades passed, engineering advanced, safety standards improved, and cableways turned into spectacular feats of infrastructure. Connecting remote ridges, carving new access routes through untouched wilderness, and powering megaprojects that reshaped the American landscape. Today, cableways are no longer just suspended transport systems. They are the arteries of mountainous megaprojects, supplying hydroelectric dams, remote construction zones, wind energy farms, and inaccessible research facilities. Their purpose goes beyond convenience. They are often the only viable solution where roads would destroy ecosystems, or where terrain makes traditional construction impossible. They reduce the need for massive earthworks, minimize environmental disturbance, and allow precision logistics in places where bulldozers and asphalt simply cannot exist. The journey of building one of these systems begins not with steel, but with information. Engineers and surveyors spend months analyzing the land using drones, satellite imaging, LiDAR scans, and advanced geological modeling. Every ridge, valley, wind current, and stress point is digitally reconstructed, allowing virtual simulations of how cables will behave under tension, snow load, and extreme weather. Even the smallest miscalculation could lead to dangerous oscillations or structural instability, so every calculation must be flawless. Once the route is finalized, the real challenge begins. Foundations must be anchored deep into bedrock to support colossal forces generated by stretched steel cables. In remote regions, helicopters ferry massive steel components through turbulent winds, while crews operate on near vertical slopes, bolting together pylons that will stand for decades. Each tower is aligned with laser precision, its angle and position dictating the entire geometry of the system. These structures are not merely supports, they are the silent guardians of an enormous aerial network. Then comes the most dramatic phase, cable stringing. Helicopters fly across the vast span, carrying a lightweight pilot line that will eventually guide multi-ton steel cables into place. Gradually, heavier ropes replace the pilot line until the main cable is suspended across miles of open air. Hydraulic tension systems carefully pull the cable to precise specifications, balancing sag, tension, and stress with extraordinary accuracy. Every second of this operation is monitored by engineers watching live data feeds, adjusting parameters in real time to ensure stability. With the cables secured, the mechanical heart of the system is installed. Massive electric motors, drive wheels, braking systems, and control units are assembled within terminal stations. These systems are capable of responding instantly to wind shifts, load changes, and emergency scenarios. Sensors continuously monitor cable tension, vibration, weather conditions, and structural performance, allowing the system to adjust automatically, preserving safety and efficiency. Finally, gondolas or load carriers are mounted and calibrated, each tested under simulated stress before entering real operation. Whether transporting tourists across breathtaking mountain vistas or hauling tons of material to inaccessible construction zones, every unit must glide with smooth precision. Extensive safety tests ensure the system can withstand extreme conditions, from blizzards and high winds to sudden power fluctuations. Behind the quiet elegance of a gliding cable car lies years of relentless engineering, risk management, innovation, and human determination. The supergiant Cableway installation process is not just about building transportation systems. It is about redefining what is possible when human intelligence meets the raw power of nature. It is a testament to how ambition and precision can transform air into infrastructure and isolation into connection. And as these aerial highways silently weave through mountains and megaprojects across America, they stand as living monuments to mankind's ability to conquer the impossible. One cable, one tower, and one extraordinary vision at a time. If you enjoyed this cinematic journey into the heart of modern infrastructure, don't forget to like, subscribe, and turn on the bell for more supergiant explorations into the world's most extraordinary processes. How machines as massive as airplanes, trains, or wind turbines can spin so smoothly without grinding themselves apart? The secret lies in one small but mighty invention: the bearing. Today we're taking you inside a supergiant bearing factory in America, where precision engineering meets raw power, and where millions of bearings are produced every year to keep our world turning. From tiny ones used in skateboards to massive ones used in wind turbines, this is a story of science, steel, and symmetry. Before we dive into the world of rolling perfection, make sure to subscribe to our channel. Every week, we uncover the incredible stories behind the world's most advanced factories, where technology transforms raw materials into everyday miracles. Every bearing begins with one essential ingredient: steel. But not just any steel. Bearings demand high-carbon chromium steel, a type of alloy that must be extremely strong, hard, and resistant to wear and heat. The process begins with massive billets, steel bars weighing hundreds of kilograms, heated to over 1 to 1200 degrees tuned to ease feel. Once glowing red, they're cut into smaller slugs, the perfect size for the bearing rings. These slugs are then forged using hydraulic presses that exert tons of pressure, shaping them into rough rings. This forging process aligns the internal grain structure of the metal, giving it superior strength and durability. Because bearings must endure constant rotation, friction, and extreme load. After forging, the rings are cooled, cleaned, and sent to CNC machining centers. Here, precision takes over. Computer-controlled lathes carve out the exact dimensions, inner and outer diameters measured to microns, thinner than a human hair. Each ring goes through multiple turning, boring, and grinding operations. The goal is to create perfectly round, smooth surfaces that can house the rolling elements, whether balls, rollers, or needles. At this point, the rings already look like a bearing, but they're still soft steel. Next comes the step that gives them their legendary toughness. To handle decades of spinning, bearings must resist deformation. That's achieved through heat treatment, a process that hardens the steel. Rings are heated again to about 850 degrees Celsius, 560 degrees Fahrenheit, and then rapidly cooled in oil baths. This sudden temperature drop transforms the steel's structure into martensite, giving it extreme hardness and wear resistance. But the process isn't finished. The rings are then tempered at a lower temperature to reduce brittleness, balancing toughness with flexibility. Now each ring can endure years, even decades, of spinning under pressure. Once hardened, it's time for precision grinding, the most critical stage in bearing production. Grinding machines fitted with diamond wheels remove microscopic layers of steel, refining each ring's surface until it's mirror smooth. The tolerances here are astonishing, within 0.0001 inches, 2.5 microns. In the world of bearings, even a speck of dust can cause vibration or noise. That's why this process happens inside ultra-clean rooms, where temperature and humidity are tightly controlled. Some factories even use automated robots to handle each piece, ensuring that no human fingerprints or particles interfere with the final surface finish. The rings are ready, but they're useless without what makes a bearing roll: the balls or rollers. Steel wire is cut into tiny cylinders, heated and pressed into rough spheres using high-speed presses that produce thousands per minute. These balls are then heat-treated and ground in rotating drums, filled with abrasive paste until they reach a perfect sphere shape. To test precision, engineers use laser gauges capable of measuring roundness to 1/millionth of an inch. Only those that pass this extreme test continue to assembly. Those rejected are melted and recycled. Nothing goes to waste. Now comes the moment of truth: assembly. In sterile assembly lines, the inner ring, outer ring, and rolling elements come together. A retainer or cage holds the balls evenly spaced to prevent contact and friction. In a single day, an automated line can assemble tens of thousands of bearings, each undergoing continuous quality checks using vibration sensors and laser alignment systems. Lubricants are carefully added, either grease or oil, depending on the bearing's purpose. Then, the seals are installed to protect the internal components from dust, moisture, and corrosion. At this point, each bearing spins with effortless motion, silent, precise, and durable. Today's supergiant bearing factories are not just about precision. They're also about sustainability. Many use recycled steel, advanced waste heat recovery systems, and coolant recycling to minimize environmental impact. Robotics and AI help reduce energy use by optimizing production schedules and detecting defects before they happen. The result? A cleaner, smarter, and more efficient manufacturing process that saves thousands of megawatt hours annually while keeping millions of machines turning smoothly. Bearings are everywhere, and without them, modern life would literally grind to a halt. They make it possible for engines to run, trains to roll, fans to spin, and even dental drills to operate. Each one, no matter how small, carries enormous importance in keeping motion alive. It's said that bearings are the heart of motion, and in many ways, that's true. Because when motion is frictionless, progress becomes unstoppable. If you found this journey fascinating, don't forget to subscribe and like this video. Thanks for watching, and until next time, keep things turning smoothly. From the shining pipes inside a skyscraper in New York to the heating systems in the freezing winters of Alaska, copper is everywhere, silently carrying water, gas, and life itself. But how do you turn a chunk of raw metal into miles of perfectly smooth, leak-proof copper pipes that can last over 100 years? Today, we'll go inside one of the world's largest copper pipe factories in America, where molten metal, fire, and precision machines work together to create the veins of modern plumbing. Welcome to the supergiant copper pipe factory, where fire becomes function and metal becomes life. The story begins deep underground. Copper ores are mined from vast open pits in states like Arizona, Utah, and New Mexico, places where the earth literally glows with metallic veins. These rocks are crushed, ground, and refined through a complex process called smelting. At over 1200 degrees Celsius, the impurities burn away, leaving behind 99.9% pure copper cathodes, flat reddish plates that shine like solid sunlight. These cathodes are the foundation of everything made in the factory. Each plate weighs around 80 kilograms, and the factory consumes hundreds of tons per day. Before heading into the furnace, they are cleaned and loaded into massive crucibles, ready to begin their transformation from solid to liquid, from raw to refined. Inside the induction furnace, copper cathodes are melted down to a glowing liquid metal. The temperature? 1085 degrees, hot enough to melt steel's soul. Every second, thousands of kilograms of copper flow through channels into continuous casting molds. Here, it cools just enough to solidify into thick cylindrical billets, about 6 inches in diameter and several meters long. Each billet is then carefully cooled, straightened, and cut, forming the raw blocks that will later become long, flexible pipes. Operators check every billet for surface flaws, bubbles, or cracks, because even the tiniest defect could cause a leak years later. These copper billets now shine like red-orange pillars of molten energy, ready for the next stage, shaping. This is where the real magic happens. The billets are reheated to around 900 degrees Celsius, soft enough to flow like clay under pressure. Then, using a hydraulic extrusion press, each billet is pushed with over 3,000 tons of force through a die, a specially shaped steel mold that creates a hollow core inside the solid billet. What emerges from the other end looks almost impossible. A perfectly continuous copper tube, glowing bright orange, sliding forward like molten silk. Workers watch closely as lasers measure the diameter, wall thickness, and uniformity of every inch. If something's even a fraction of a millimeter off, the tube is automatically rejected. The copper cools quickly as it moves along conveyor belts, slowly turning from fiery orange to metallic red. This extrusion line can produce hundreds of feet per minute, creating miles of copper tubing every hour. But the copper pipes aren't done yet. To achieve the exact size and mechanical strength needed for plumbing, they must go through a process called cold drawing. The tubes are first cleaned and coated with lubricant. Then, they are pulled through smaller dies, one after another, reducing their diameter while increasing their length.